Hello, everybody. So today we are going to move on to a new chapter. And after this chapter, we'll be taking a summative exam. There's three concepts in this chapter that all have to do with how we apply derivatives. This is going to be the most important part, as seeing as how this course is applications and interpretations. We want to know how can we apply this to real-world situations. So today we're going to focus on rates of change. Hopefully you already understand that the derivative represents the instantaneous rate of change of some function. Today we're just going to put that in context and try to solve some problems. So there's a couple ways to write the derivative, right? One way we've been writing it is dy dx, which is, basically just comes from delta y delta x. And the reason, delta was change in y and this delta is change in x. So change in y of change in x is basically slope, right? So we're talking about slope at a point, right? Hopefully this is not new. It's also the slope at a point, slope of a tangent line. And then it's called the instant rate of change. Whereas if we do the typical slope formula, this is the average rate of change, right? So there's two different rates of change, average and instantaneous. Derivative tells us the instantaneous, right? What is the rate of change at a single moment in time? Whereas this one tells us over a period of time. Okay, first kind of rate of change we're going to talk about is time rates of change. This means that something is changing as time changes, right? So we could imagine if we had some function h of t that modeled the height, and let's give the height in, I'm just going to specify units in meters above the ground of a person riding on a Ferris wheel. Then dh dt will represent the person's the rate of change of the person's height with respect to time, right? And so what we need to know is what is t measured in. Let's say t is measured in seconds. Then when you have dh dt, the unit for any answer you get in the derivative would be whatever the unit for the height is, which would be meters, and the unit for down here would be whatever the unit for time is, which in this case would be seconds. And so if you had a function, right, let's imagine, I'm just going to make something up. Let's imagine you had h equals, I don't know, 2t squared. I'm just making up something really simple, right? Then dh dt would equal 4t, right? And then if I say, well, what happens when t equals 1, right? We could write that like this. dh dt when t equals 1 is 4. The units for this would be 4 meters per second, right? Meaning the person is going up 4 meters every 1 second. And so at that exact time of, sorry, this should have been 1. If I was plugging in 1. At the exact time of 1, the person's rate of change was 4 meters per second. Okay, I might have some other model called C of t that represents the capacity of a person's lungs. So when we're thinking about what is the capacity of somebody's lungs, then you should probably say C is going to be a volume. So you might do centimeters cubed, which is a milliliter, right? So maybe we're talking about milliliters. But is a volume, and then as t, maybe let's do this in minutes this time, just so we can see that it makes a difference, right? So I could have some function c of t that equals, I don't know, I'm just making this up right now, right? If I find dc dt, right, that another way of writing that is c prime of t. I would get this. And then if I wanted to know, c prime of 1, I'll just make it simple again, I would get -5. And the units for this -5 would be milliliters per minute. And what that's saying is that at 1 second, 1 minute, because my time was in minutes, the rate of change of the volume in the person's lung is -5. So they're losing 5 milliliters per minute at that exact moment in time. Another example might be if you were thinking about maybe like a tree and you have like a squirrel running up the tree. Maybe you could write a function for how far up the tree he goes, right? So you could say, oh, well, I'm going to call this the position. The position of the squirrel after t seconds is equal to, I know maybe you can make something up. Let's just say 2t to the third plus 5t, right? And so, you know, we could plug in numbers and say, oh, well, how is the squirrel at time equals 0? At time equals 0, if you plug in 0, you get 0. So at t equals 0, the guy was down here. And then you could say, okay, well, after 1 second, where was he? You could plug in 1 and you get 2 plus 5, 7, right? At t equals 1, he was at 7. He was 7. Let's say this is measured in, I don't know, let's just do it differently. Centimeters, and let's say time is measured in seconds, right? So he was, at time equals 1, he was 7 centimeters up there. And then, you know, at time equals 3, you'd plug in 3, and you'd figure out how high up he was after 3 seconds, right? So we might want to know, well, how fast was he climbing at t equals 2.5, right? Like right there, how fast was he moving? So we could find the rate of change, the dp dt, right, which would be the derivative. And then we could say, okay, well, at 2.5 seconds, we plug in 2.5. This would tell us how fast he was traveling at exactly 2.5 seconds. And if you do this, you end up with 42.5. And again, we want to think about what are the units. Well, the units are dp. P was measured in centimeters, and our time was measured in seconds. So he's moving at 42.5 centimeters per second. And this is contrasted with, what if we said, well, what was his, and you notice centimeters per second, that's like a velocity, right? It's like meters per second or kilometers per hour. That's a velocity, right? So that's getting some physics connections. Another question that we should be able to answer is, what was his average rate of change between 0 and 2.5 seconds, right? And so in this is the case where you do p of 2.5 minus p of 0 over 2.5 minus 0, right? And so if you plug in, and again, when we're doing average rate of change, it's really important to understand that you're plugging this into the original function, not the derivative. And so if you did p of 2, if you plugged in 2.5 to the original function, you would get 43.75. If you plug in 0, you get 0, and then 2.5 minus 0 is also 2.5. And so in this case, you would get 17.5. And again, just think about your units, right? The p function was given in centimeters, and this was time, centimeters per second, right? So the average rate of change is 17.5, right? Because basically it starts kind of slow, and then he starts going really fast once it gets up there. Okay, that's about all we're going to do for today. I just wanted to make you aware of something so you don't make this mistake. If I have this, and I want to find the derivative of this, how do I do it, right? I think a lot of people are going to be tempted to be like, oh, dy dx equals 2 x minus 2 to the 1. And actually, I'm going to change this a little bit. I'm going to make this to a 2 because then that'll change it a little bit. And this is wrong. That is not correct, right? Power rule doesn't work when you have a big mess of things under here. So you actually need to like multiply this out, which you should remember how to do. Right? If you do this, you get 4x squared minus 4x minus 4x plus 4. And then you can take the derivative. Right? Which is different than here we would have gotten 4x minus 4. Right? That's not the same as 8x minus 8. So just be aware, if you have like parentheses and stuff, you can't just use power rule. Power rule only works if you have single terms with exponents, right? It only works for things like this. It does not work for things like this. Okay, so just be careful about that when you go through this.